Welcome back. Problem number 59 from chapter 21 gives us another opportunity to analyze a heat engine. Specifically, and I should have said this in the previous video, specifically an ideal gas heat engine. Those are the only heat engines we're considering, because if you are dealing with water, which turns into steam, liquid water, which turns into steam, then you're talking about phase changes, and that's more complicated. I've actually never taken a course where I learned how to analyze such engines. So we will only be dealing with ideal gas heat engines. And in order to solve this problem, there's another formula that we need to add to our toolbox of formulas for ideal gas processes. You want to have all those formulas on your note card ready to go. So let's introduce the last one right now. But before I do that, I'd like to revisit a point I keep making, because I made it in a way in the previous video that's less than perfectly clear. So I'd like to clear that up. And that's calculating the change in energy for an ideal gas using the constant volume specific heat, or molar specific heat. Suppose you're taking a gas from this point on the PV diagram to this point. In general, you've moved from one isotherm to another. And let me draw the isotherms. You know what? I should have put these closer together. All right, ignore that dot. Let's say the second state is right here. So there's an isotherm on which the first point lies. And here's another isotherm. And we know that as you go outwards from the origin, you're crossing isotherms of higher, or corresponding to higher and higher thermal energies. And regardless of the means by which you took the gas from here to here, whether it was, whether it was an isobaric process or an isochoric process, that's actually not possible, is it? There's no way to get from here to here on an isobaric or through an isobaric process. That would be a horizontal line, and an isochoric process would be vertical. So I'll just draw an arbitrary path on the PV diagram from state 1 to state 2. Now, obviously, because we're on different isotherms, the thermal energy of the gas changed in going from here to here. But remember, because the thermal energy for a given number of moles, the thermal energy depends only on the temperature, then a gas at this point on the PV diagram would have the same energy as the gas here. So if you were to calculate the change in energy going from here to here, this constant volume process, that change in energy would be the same as the change in energy required to go from here to here. Kind of a subtle point, but really valuable. The change in energy for this process is the same as the change in energy for this process, because you begin and end on the same isotherms, and temperature is the only thing that determines energy for an ideal gas. So let's look at the change in energy going from here to here. I'll call this temperature T1 and T2. We use the first law of thermodynamics, which says, let's see, how do I want to write that in this case? I'll say the heat transferred into or out of a gas shows up in two ways. Oh, I want to do it this way. Let's go with the pre-chapter 21 way of writing it. You can change the energy of a gas two ways. Do work on it. Your book just calls that work W, or transfer heat to it. For an ideal gas, nope, not for an ideal gas. For an isochoric or constant volume process, no work is being done. If the gas is not expanding or contracting, being compressed, no work can be done. So that's zero. And then the change in energy is merely the heat transferred. But specifically, that would be the heat transferred at constant volume. Well, we have a formula for that. It's the definition of constant volume molar heat capacity. So for constant volume, in which case no work is done, the change in energy is just the heat, and that would be number of moles times the molar specific heat at constant volume times delta T. And just look at the beginning and ending of that equation. Again, it doesn't matter how you got between the two temperatures. It doesn't matter if you went between these 2 points on the isotherms or these 2 points. The change in energy is the same in either case. That's why we can always use this to find delta E for an ideal gas. If it's not an ideal gas, then these are not going to be equivalent. But fortunately for us, that's the only type of substance we are looking at in this chapter. Okay, so now let's calculate the work done in an adiabatic process. And I'll call that WS. So now we're taking the chapter 21 perspective. We're talking about the work done not on the gas, but by the gas. That's the work done by the system. WS for an adiabatic process. That's our last formula, because you don't actually have that formula yet, unless you've been doing your reading. I certainly hope you have. Okay, for an adiabatic process, and I'm going to rewrite the first law now using the new notation. All we've done is exchange W for negative WS, and we get to this. Again, if you impart heat to an ideal gas, that can show up in a couple ways. Either the gas can use it to do work, or it'll just change the internal energy of the gas. What's the definition of an adiabatic process? Well, it's a gas that's insulated from its environment, in which case no heat can flow in and out, or it's a process that happens so quickly there's no time for heat transfer, because it does take time for heat to be transferred. Either way, the heat is zero. And that means that the work done by the system is merely the negative of the change in energy. Beautiful. So if we could come up with a formula for the change in the energy, that would be the work done. Well, we have a formula for the change in energy. We can always imagine that we were moving between the two temperatures using a constant volume process, and then just set that equal to NCV delta T. Don't forget the minus sign. NCV delta T. Well, if this is a process involving a fixed quantity of gas, then N doesn't change. And that means we can put N inside the delta sign. I can write it as delta NT. See that? This would be NT final minus NT initial, factor out the N, and it's exactly what we've got here. And then I'm going to do something further. Well, yeah, how about I do, I'll put, let's try this, CV over R. I've divided by R, and I have to pay for that by multiplying by R. And again, because R is a constant, it doesn't change. You can also put that inside the delta. This is a lot like how you can pull a constant in and out of a derivative. But NRT should set off an alarm in your head. You should think, oh, that's PV. PV equals NRT. So since PV is the same as NRT, then NRT final minus NRT initial would be the same as PV final minus PV initial. So that means that the work done is now negative CV over R times the change in the product PV. And we're almost at the formula for the work done by a gas in an ideal gas in an adiabatic process. So the last thing would be, can we rewrite this somehow? And hopefully you're already thinking, I've seen that before, the ratio of constant volume molar heat capacity to R. Remember, definition of gamma. Gamma is the ratio of the heat capacities. It's CP compared to CV, but we know that for an ideal gas, CP is just CV plus R. Okay, this fly has been bothering me. I'm going to get it right now. Okay, I don't think I got him, but I at least scared him. Down here is CV. Okay, CP is CV plus R. And then let's go ahead and distribute. CV over CV is just 1. So I could also write gamma as just 1 plus R over CV. And that means that gamma minus 1 is the same as R over CV. Well, lastly, I'm going to flip the left side, which amounts to multiplying both sides by negative 1. So if I just flip these, 1 minus gamma, that's the same as negative R over CV. And I'm doing that because, check it out, here's a negative CV over R. Negative CV over R is the reciprocal of this. So in other words, this quantity can be written as the reciprocal of 1 minus gamma. Everybody see that? Not like you're going to answer me here, but I've just identified this as the reciprocal of that, which is the reciprocal of 1 minus gamma. So the work done would be the reciprocal of 1 minus gamma times the change in PV. And you could write it like that. That's perfectly, whoops, out of frame. That would be perfectly valid to write it like that. Now your book, they go ahead and write this as final minus initial. So you could also say It's P final, V final minus P initial, V initial over 1 minus gamma. However you want to write it. I think this is fine. So when can you use this? It's for an adiabatic process only for an ideal gas. And the problem that we're going to look at now, the homework problem, has just such a process in it. Now, this problem does not come with a series of pictures the way problem number 35 did. So we don't have the benefit of little cartoon pictures showing a flame underneath a cylinder with a piston. That was actually the tricky part of that problem anyway. So we are given a PV diagram. So let's try to infer a couple things about when heat is added or taken away. We start at 0.1 on the PV diagram. We can just read off the graph the values of the volume, the pressure, and the temperature. Ooh, there's that fly again. Okay, this time I got him, but he's got a buddy who's still on the loose. We can also read the temperature right off the graph. They give it to us. It's not really on the graph. It's a separate label here. 300 kelvins is this bottom isotherm. So one thing that makes this problem, on the one hand, simpler than problem 35 is that we only have 3 different points. There's 3 vertices for this closed trajectory in the PV diagram. And as I pointed out earlier, the only cycles we can really analyze are ones for which every process is one of those special processes. So here we've got 1 isochore, 1 adiabat, and 1 isotherm. You can see this has to be an adiabat because if it was an isotherm, it would never intersect this other isotherm and you wouldn't be able to close the cycle that way. But because an adiabat is steeper, it will intercept the isotherm. So like I said, you can play around with inventing your own closed PV cycles comprised only of these special ideal gas processes. And you should be able to analyze all of those with the tools that we have available. Okay, how could you raise the pressure of the gas between points 1 and 2 without changing the volume? You've got those particles bouncing around in a box. You're not going to compress the box, and yet the pressure goes up. You would have to make the particles go faster, and that means increase the temperature. So we can use that proportional reasoning and or the ideal gas law to figure out what the temperature is for this point. There's going to be another isotherm going to that point, and that isotherm is not this curve. This is an adiabat. Let me get my laser pointer here. So there would be an isotherm passing right through here that's not as steep as this adiabat. Now, the thing is, if we're going to use that proportional reasoning to get this temperature using the change in pressure, well, first we have to find the pressure up here. We can't read it off the graph. They didn't actually label it. Here it's clear that the pressure is 400 kilopascals, but if we go over to the left here, it's not labeled. So if we can't relate these 2 points to get the pressure, we're going to have to relate these 2 points to get the pressure. Now, at point 3, we do know all the variables. We know the volume. We just read it off the graph. We know the pressure. And it's on the same isotherm as point 1. So we also know the temperature. And that means we can also solve for not solve for. We already know the pressure. We could solve for the number of moles. But we should be able to relate these 2 points to find the pressure up here. P and V is the way to do that. Remember, we've got a couple formulas for constant quantities in adiabatic processes. So let's review those. For an adiabatic process, it's understood. We're talking about ideal gases only. We've got the P1V1 to the gamma equals P2V2 to the gamma. What's the other one? T1V to the gamma minus 1 equals T2V2 to the gamma minus 1. I'm checking the book here. Yes, that's correct. And then there's a third one relating T and P. And you know how I remember that that's the troublesome one? Because remember, that the exponents for that one are trickier. That's why your book doesn't even write it down. You could combine these to get the relation involving T and P. Here's how I think about it. I just think back to the early weeks of coronavirus. No TP, right? Same here, no TP. There is a relation between T and P, but we don't have it in our list because it's kind of messy to write down. Hey, you're welcome to throw it on your note card so you don't have to rederive it. That would be fine. And because if you think back to the graph that I just showed, at point 3, we knew the pressure and the volume. And at point 2, we knew the volume, we can solve for the pressure. So for this particular problem, let me pause and go right back to the graph. We're going to relate 0.2 and 0.3. So instead of P1 V1 and P2 V2, I'm talking about P2 V2 and P3 V3. P2 V2 to the gamma minus 1 equals P3 V3 to the gamma minus 1. We're solving for P2. That's the one that's not labeled on the graph. So that's going to be P3. Just take P3 and multiply it by this ratio, V3 over V2 to the gamma minus 1. Now, I'll go back to the graph once more. If you hear me clapping, it's because I'm trying to activate the mic. Just ignore it. Even though we're going clockwise around this cycle, which tells us we're talking about a heat engine, probably not a refrigerator, you can imagine doing this process in reverse. If you had the gas occupying this many milliliters, and then you compressed it all the way down to 1,000, from 4,000 to 1,000, if that's an adiabatic compression, no heat can go in or out, then you would expect the pressure to shoot up. So we know that P2 should come out higher. How much higher? Well, that ratio will tell us. V3 was the 4,000, V2 was the 1,000. So we have a ratio of 4 to 1 in here, and we're raising it to a power. So yes, P2 will come out greater than P3. Now for a diatomic gas, remember the ratio of the heat capacities, that's Cp over Cv. Well, for a diatomic gas, we're talking about 5 degrees of freedom at normal temperature. So that's 5 halves R, add R to get Cp. So that's 7 halves R. And the 1 halves cancel, and we get a ratio of 7/5, which is 1.4. So you see that 1.4 a lot because often we're talking about ideal gas heat engines where the working substance is air, and air consists of mostly nitrogen and oxygen, both of which are diatomic. Okay. You know what? I could proceed to do this on paper, and you should, but I would like to use a spreadsheet. So let me pull that up. Here's my template spreadsheet, and I've erased all the work. I already did the work to make sure that this works out fine, but I've erased it so you can see the process from the beginning. Let me fill out the constants that we'll be using. We know that the ideal gas constant 8.31 in SI units. Cv, because we're talking about a diatomic gas at typical temperatures, it's 5 degrees of freedom. So this will equal 5 times R over 2, 5 halves times R. That's that familiar number. And we know that Cp is Cv plus R. So instead of doing the 7 halves, I could just say this equals, equals Cv plus R. That works. And then gamma is the ratio of the two. So this would be Cp compared to Cv, and Cv is in cell C2. There's the 1.4 that we expect. In problem 35, we had 4 different points. This is a little simpler in that regard, just 3. And let's plop in all the information that we can read off of the graph. So let me pull that back up. Try to remember all of it at once here so that I don't have to keep switching back and forth. What information do we have? Well, for points 1 and 3, they're on the same isotherm. That's at 300 Kelvin. So we don't even need the ideal gas law to find that temperature. It's given to us. We really don't know anything about point 2 except for the fact that it's got the same volume. So points 1 and 2 both have a volume of 1,000 milliliters. And point 3 is over here at 4,000 milliliters. Also, the last piece of information we need is the pressure for these 2 points. The pressures we're talking about are 100 and 400 kilopascals. So see if you can remember that. And then I'm just going to throw that all into the spreadsheet right now. What do we know for point 1? It was at, oh, see, I've already forgotten. How bad is that? Was that 100 kilopascals? Hang on a second. No, that was the 400 pascals. Okay. So the pressure at point 1 is equal to 400 kilopascals, so times 10 to the third. And that volume was 1,000 milliliters. So it equals 1,000, and a milliliter is a millionth of the SI unit of volume, 10 to the negative sixth cubic meters. The temperature we're told was 300 kelvins. Now 0.3 on the other side was also at 300 kelvins. Remember, that was at the same, or on the same isotherm, but the volume was 4 times as much, 4,000. I could just do this. Excuse me, I could say 4 times this volume. We know that 0.2 shared the volume with 0.1. They were on a single isochore. Am I leaving anything out? We don't yet know the temperature after that isochoric increase in pressure. We don't yet know the pressure at 0.2. As for 0.3, that was the one that was down at 100 kilopascals. So every problem is different. You know, which information is given, that's going to depend on the problem. But I believe I've entered everything that was given in the graph. And it's up to us to use our toolbox of formulas for ideal gas processes to fill in the rest. And I neglected to mention, as I often do, what we're trying to do here. The problem asks us to basically complete the table, find the work done for every process, the heat in or out for every process, the change in thermal energy, and lastly, what's the efficiency of this engine? That's the interesting part, right? Because if you just showed this graph to some random person off the street, or the average member of the public, they would have no idea of looking at a graph, figuring out, or how to look at a graph and figure out how efficient an engine is. So it's cool that we can do that. It's a process to get there. But the fact that we can use math and these results, which first of all were derived almost experimentally long before the 1900s, and then re-derived using the kinetic theory of gases. There's just so much that goes into this. You know, you've been learning stuff for weeks, all of which culminates in the ability to analyze these ideal gas heat engines. Okay, I just got that fly's buddy. It should be peaceful in here now. Is there anything we can fill in here first? Well, remember, just a moment ago, I looked at the adiabatic process from 2 to 3. I related these 2 points using the equation with PV to the gamma, and I found that P2, so let me fill this in right now, P2 was equal to P3 times the ratio of the volumes, that's volume 3 compared to volume 2, I have to type it here, raised to the gamma power. So caret raised to the gamma power. I'll click on the cell for gamma. And that looks familiar. Your solutions manual has that number. So notice that you can't use simple proportional reasoning there. It's not just, you know, if you double the volume, then you've doubled the pressure. It's because of that exponent, the gamma exponent. You really do need a calculadora to do that. Now, as for the temperature at state 2, again, we could use the ideal gas, the Perver-Nernst law, but because we now know the pressure, we can use proportional reasoning. If your box is staying the same, going from state 1 to 2, that vertical upwards isochore, since your box is staying the same in volume, those particles bouncing around are going to have to be hotter in order to produce more pressure. And the ratio of the temperatures will just be the same as the ratio of the pressures. So this temperature is equal to the previous temperature times the ratio of the pressures. The pressure at the top of the isochore compared to the pressure at the bottom of the isochore. Now we know the temperature in kelvins at 0.2. It lies on the 522 Kelvin isotherm. Okay, now that we know all these, we should be able to proceed with the rest of the table. Now, it's not clear yet if we need the number of moles. Probably will for calculating heats. But let's go ahead and calculate that. Again, in your head, PV equals nRT, so N is PV over RT. Pick one point on the PV diagram and apply that formula. So N is equal to PV, I'll go with 0.1, P1 times V1 divided by RT, which is the same as divided by R. Let's see, R is in cell C4. Divided by T, I was using 0.1, so that's T1. Now we know how many moles we're talking about. Less than 1 mole. Excuse me. Okay. Now, just as in problem 35, I've made 2 columns for work so that I can check my calculations by calculating the work in some alternate fashion. And you don't have to do it this way, because really it depends on the problem. You know, which of these you could do in an alternative way is going to depend on the problem. Sometimes it's the change in energy that you could calculate in two different ways, not necessarily the work. So don't get too attached to this way of doing things. At the very least, you need 3 columns, one for the work, one for the heat, one for delta T. And please do me a favor. If you're talking about the work done by the gas, let's stick to this, to the notation that your book uses. Call that WS, work done by the system, because it does affect the pluses and minuses. Okay, process 1 to 2. Hopefully you've got that picture in front of you. That was the isochore, straight up. That's easy. Isochoric processes involve no work. There's no expansion or compression. And again, isochore is constant volume. How much heat is required for a constant volume process? Well, that would be the definition of constant volume, molar specific heat. So this is going to equal the number of moles times the constant volume heat capacity for an ideal or a diatomic ideal gas times the temperature difference. So how much did the temperature change in going from state 1 to state 2? That would be T2 minus T1. Now I want to watch the Terminator. Delta E. There's a couple ways you could do this. So let me go back to my notes. You could always use this for an ideal gas. You can say that the change in energy is number of moles, constant volume heat capacity times delta T, because this is true regardless of whether your process was constant volume. But in this case, our process actually was constant volume, and we just used this to find the heat. So doing it this way is equivalent to recognizing that, let's see here, I have to like switch back and forth between these two ways of writing the first law. I'll use the chapter 21 version. If it's a constant volume process, then there is no work being done by the system, and then the change in energy is merely equal to the heat. So back to Excel, back to the warm comfort of the spreadsheet. I'll just say that the change in energy is the same as the heat. Okay. And sometimes it's nice to pause and think, do these numbers seem reasonable? We've got less than a mole here. It's not a lot of gas. It shouldn't take that much energy to raise the temperature of a gas. We're raising the temperature by, over 200 degrees. So I guess it makes sense that we're using this many joules, because remember, 4,000 joules roughly is a food calorie. So we're talking about 1/5 of that, maybe 1/6. Okay. Where was I? Moving on to the adiabatic process. Can we calculate directly the work done in an adiabatic process? As a matter of fact, we can. Remember, we just developed that formula. It was it's the change in PV over, and now I forget, is it 1 minus gamma or gamma minus 1? It's 1 minus gamma. If you're going to do the work done by the system, then the denominator is 1 minus gamma. So let me go ahead and just implement that formula. This only works for an ideal gas, for an adiabatic process. Don't try to apply this formula for an isobaric process. It's not going to work. Besides, there's a simpler formula for isobaric. So here we go. This would equal the change in PV. So that is PV final. It's the final state would be state 3. So pressure 3 times volume 3 minus pressure 2 times volume 2, because our initial and final states are states 2 and 3. Let me enclose that in parentheses. That's the numerator. And we're dividing that by 1 minus gamma. So let me enclose that in parentheses. The denominator 1 minus gamma. Interesting. The work done along the adiabat is numerically equal to the heat drawn up during the isochoric increase in pressure. Let's look at the PV diagram and see if that makes sense. As we go from state 1 to state 2, the pressure is only increasing because heat is flowing in. I think at the first law, if obviously temperature is increasing because we're jumping from one isotherm to another. There's that other isotherm going through here. And that means the energy is increasing. Well, we're not increasing this gas's energy by doing work on it because it's an isochoric process. So the only way that the energy is being increased is by a flow of heat in. So this is where the your heat engine, or the working substance of your heat engine, is drawing in heat from the high temperature reservoir. And we just found in the spreadsheet that immediately that quantity of heat goes into doing work. I think it was 741 joules of heat are taken up, and those 741 joules are immediately used to perform useful work. Okay, so that's not always the case. Very often along the next process in the cycle, it's some different quantity of work being done. They don't have to be equal, so don't get too attached to that. Let's finish filling out this row. Okay, the heat exchanged for this adiabatic process. Is there a formula for that? Oh, there is. It's 0. That's the definition of adiabatic, right? No heat. That one was easy. Now, we could use the first law now to recognize that since there's no heat, if the gas is doing work, if the substance is doing work, then it's losing energy because that work is not being replaced by the flow of heat. So if the gas does positive work, then the gas just lost internal energy. Just think of like your body. If you exercise all day and you don't eat, you lost the sum of the chemical energy within your body definitely just went down because you didn't replace those calories with food intake. Same thing here. So the change in energy is just going to be the negative of the work done because there's no replacement with heat. I could do it that way, but let's try something else. That, by the way, that was an implementation of the first law of thermodynamics. Let's do it the other way and use that as a check. So we can always use this. The change in energy should be the number of moles times constant volume heat capacity, even though this was not a constant volume process, but we have to use the appropriate temperatures. So since we're talking about process 2 to 3, final temperature is T3, initial temperature is T2. Voila, of course they're the same. 3 to 1, that was the isotherm, right? We're going back along that isotherm on the bottom of the cycle. Is there heat exchanged in an isothermic process? Yes. The trivial one in this instance is delta E. Remember, for an ideal gas, if there's no change in temperature, there's no change in energy. So as you move along an isotherm, delta E is 0. Great. So all we have to do is calculate one of these and solve for the other. Which one do we have a formula for? Did I just end a sentence with the preposition? We have a formula for the work done. And I'll just refresh your memory because you're going to need this. The most general way of calculating the work done by the substance or system is to get the area under the PV curve. And remember, if you're doing WS, not W, it's positive integral of P dV. Well, P, if you use the ideal gas law, P would be nRT over V dV. But if it's an isothermal process, T is a constant as well as N and R, so pull out the constants, integral of dV over V. The antiderivative there would be the natural log. That's where you get the natural log of the ratio. Remember, when you evaluate at your upper and lower limits, the difference in two logs is the log of the quotient. That's fun to say. The difference of the logs is the log of the quotient. Back to the spreadsheet. Okay, so the work done by the system is nRT log ratio of the volumes. Number of moles times R times the temperature. Okay, which temperature do we choose? We're on that 300 Kelvin isotherm, so it really doesn't matter if I use state 1 or state 2. Times ln, I believe Excel uses just ln. Yes. Why is it ln and not nl, natural log? It's French. It must be French, right? Logarithm natural. That's terrible. Just go back and just mute that part of the video if you ever watch this again. Natural log of the ratio of the volumes. And that's got to be final minus initial. The order is crucial. Final, or I should say final divided by initial. So in this case, since we're going to the left along that isotherm, it's a clockwise cycle. The final volume would be volume 1. Be careful there. And the initial volume is V3. We started at 3 and went to the left towards 1. Okay, now does it make sense that the work is negative? Why don't we go back to the graph once again? I would say it does make sense because the gas is being compressed. If you're compressing the gas, you're doing positive work on the gas. That means that the gas is doing negative work. We do expect a negative number. And now that we know 2 of the 3 quantities, we can use the first law to find the third. Well, how do you want to think? You could just use the equation, but let's also try to reason through it. Okay, so if you're compressing a gas along an isotherm, its energy is not changing. Now, generally, when you compress something, don't you increase its energy because you're squeezing it? You know, you're doing work on it. So if you're compressing this gas and yet its energy is not changing, then it must be shedding heat as it's being compressed. It's because you're putting energy into it by doing work on it, and that energy is just going right out the back door in the form of heat. So this heat would have to be equal to Ws. Now it's the negative of the work done on the gas, right? I just said we do positive work on the gas, but the heat flows out, so it's negative. But the negative of the work done on the gas is the work done by the system. So we just set them equal to each other. Now, if you really want to use the equation, which you probably should, you just go back to this version of the first law, the chapter 21 version, as I'm calling it. If you put heat into a gas, that can either be used to do work by the gas, or it raises the gas's internal energy. Isotherm, no change in energy, they're equal. Back to the spreadsheet. Okay. I'll just go ahead and I'll just leave these blank, I suppose. And we're done. This PV cycle only had 3 vertices, if you want to call them that, so we're done. The network would be the sum of all of these. Along each process, the gas might be doing positive work, negative work, or 0 work. The total work done by the gas is the sum of all of these. And this is what we call W out, right? The notation depends on which direction you're following the PV cycle. Clockwise is a heat engine. And a heat engine, the whole purpose is to do useful output work. So this is really W out. If it was a refrigerator, if we were running this in reverse, we would probably call this work W in. And it's a positive quantity, right? It had better be a positive quantity. Why would you want a heat engine to do negative work? Perhaps there's an answer to that. And also, I will point out now, but there's a surprising result in another homework problem that I'm going to look at. Running a heat engine in reverse does not necessarily give you a refrigerator. You know, a refrigerator is something that draws heat from a cold reservoir and puts it into the hot reservoir, opposite the direction heat normally flows. You need input work to do that. It's not going to happen by itself. That would be a violation of the second law of thermodynamics. But that's the whole point of a refrigerator. And a refrigerator is like a heat engine in reverse, but not all heat engines in reverse are refrigerators, which I thought was a little surprising. Okay, the net heat, again, is just the sum of all the heats, including signs, right? You have to include the signs. And we expect, remember, a heat engine has a working substance that goes around a closed cycle. It should begin and end at the same state. There should be no total change in energy. And we can see that easily. And so now apply the first law of thermodynamics to the entire system. We applied it piecewise along each individual process. It's valid along each process, but it's also valid for the cycle as a whole. Whatever heat you dump into the gas throughout the cycle is being used, all of it is being used net to do work. And since it's a closed cycle, we don't expect any change in energy. So the net heat that's taken up by the heat engine's working substance is used to do output work. That's one of the sources of confusion with these problems is Q can mean several different things. Are you talking about the heat for an individual process? Is it the net heat for the whole cycle? Is it QH, which is actually an absolute value? It's the sum of the absolute values of the positive Qs. So make sure you understand what the various uses are for these letters. Now we're ready to calculate the efficiency. And remember, let me show you the notes. Just think about it in common sense terms. The efficiency eta of a heat engine is how much useful work you get compared to what you had to pay for. Well, what you have to pay for is the heat that comes from burning the coal, burning the oil. So it's the output work, or W net, divided by not the net Q, but QH, the heat that was absorbed from the hot reservoir. And QH, I'll put, it's the sum of the positive individual Qs, because the positive Qs are when heat was being transferred into the working substance. And this, I'd have to think about it, but this statement is not necessarily true for a refrigerator. In fact, it would not be, as I think about it. Yeah, it would not be true for a refrigerator, because the heat dumped into the hot reservoir would actually have a negative sign from the perspective of the working substance. So this is only applicable to heat engines. Back to the spreadsheet. Sorry for the pause here. Okay, so the efficiency here will be the output work, that's the net work done, compared to just the sum of the positive heats. Well, for this particular problem, I only see one positive heat. It's that during the isochore, the working substance absorbed the 741 joules from the hot reservoir. And there it is. That's not too bad. 25% efficiency. I think that's a typical value for like an internal combustion engine like you find in your car. So I'd like to point out this 0.25 or 25% efficiency is markedly higher than the one we found from problem 35. Remember, I was poking fun at that stupid boxy square rectangular PV cycle, and because they had that lousy efficiency of 12.5%. Let's go back to the diagram here. The shape of this PV cycle in the PV graph or diagram is not as simple as that rectangle. It's got some curves here, with the exception of the isochore. So evidently, switching from straight line paths in the PV diagram to these adiabats and isotherms tends to increase efficiency. That's just a general observation I'm making here. It's not like a law. That's not a thing that I've discovered mathematically. Perhaps by getting rid of this isochore, we could make the engine even more efficient. So we'll get to that shortly. Hopefully in the next few days, I can do a video about the Carnot cycle, which consists solely of adiabats and isotherms. So it's got kind of a slivery shape in the PV diagram, and it ends up being the most efficient possible engine. So maybe you're making the observation that I'm making. It's kind of surprising that because the box looks like it encloses more area in the PV graph than does this PV cycle, and yet this PV cycle corresponded to greater efficiency. So remember, the area enclosed corresponds to what? That is the useful output work. The output work is the area enclosed. So you can ask yourself, for this given arc length here, if you could roll this out flat, maybe it's 10 inches long, you could ask, okay, what shape could you make with 10 inches of arc length that would enclose the maximum possible area? It's obviously not this shape. This is almost closed. It would be a circle, or not as good as a circle. It could be a box. If you made a box with a perimeter of 10 inches, that would definitely enclose more area than this, which means it would correspond to more useful output work. So are you thinking there's a contradiction there? If the box actually, for the same arc length, if the box enclosed more area, that means more output work. Wouldn't that be better than this? No, because what we haven't taken into account is, or what I have not taken into account here is how much heat had to be drawn up to do that. So supposing you did construct an engine whose PV cycle, whether it was the box or this shape, had the same total arc length, yes, you would get more output work for the boxy PV. I'll just call it the box cycle, but you would also have to pay for more QH. You'd probably have to dump in considerably more coal or oil to get that output work for the box. In fact, you just compare the efficiencies, right? The efficiency for the box was, if I remember, 12.5. This was 25. Okay, so soon we will seek out the shape of the PV cycle that maximizes efficiency. Interesting question, is it not? And I'll ponder one more thing here. Some of you might be familiar with coordinate transformations. Yeah, I should have rehearsed this thought, but let's see here. Think about the isochore here. If this was an XY plane, wouldn't this be a line of constant X coordinate? Every point on here has got a constant X coordinate. In this particular graph, every point has a constant V coordinate. Well, those are obvious, vertical lines, horizontal lines. Those are obviously lines of constant X or constant Y. But check it out, this hyperbola here is a line of constant T. And the adiabat, well, that's not so obvious, but maybe there's some other quantity we haven't defined yet for which that quantity doesn't change as you move along an adiabat. Because there is no such thing. And it's not Q, because Q is not a function. Q is energy in transit, and Q is 0 for an adiabat. But since there's this quantity called absolute temperature, which does not change its value as you move along this isotherm, perhaps there's some other quantity which does not change as you move along an adiabat. And you know what? I think it might be entropy, believe it or not. So constant volume is a vertical line in a PV diagram. Maybe there's some other graph you could draw with different coordinates as your axes where constant temperature was actually a horizontal or vertical line. And I think I've just answered my question in this rambling here. I have seen S versus T graphs. Those are entropy versus temperature. Maybe on S versus T graphs, the isotherms and adiabats are horizontal and vertical lines. Don't quote me on that. If you're curious, hopefully you'll explore that. If you're a physics major, maybe you'll see that in the future.